Evaluate the composite functions. First we have sine of inverse tangent of t divided by 5. Starting with the inner function, inverse tangent of t divided by 5 equals some angle theta whose tangent function value is t divided by 5. However, we don't know whether t is positive or negative, and recall that the output of the inverse tangent function is the open interval from negative pi divided by 2 to pi divided by 2, which indicates we don't know whether the angle theta terminates in the first quadrant or the fourth quadrant. Let's go ahead and sketch a reference triangle in the first and fourth, as well as the fourth quadrant. This would be the angle theta in the first quadrant. This would be the angle theta in the fourth quadrant. In either case, because the tangent function value is t divided by 5, we know y divided by x, or the ratio of the opposite side to the adjacent side, is t to 5. Let's label the opposite side t and the adjacent side 5. In the first quadrant is when t is greater than 0. The fourth quadrant is when t is less than 0. And now to evaluate the composite function, we want to determine the sine of the angle theta, which is equal to y divided by r, or the ratio of the opposite side to the hypotenuse, which means now we need to determine the length of the hypotenuse, which will be the same for both reference triangles. Let's go ahead and label the hypotenuse r. Using the Pythagorean theorem, r squared must equal t squared plus 5 squared for both reference triangles, which gives us r squared equals t squared plus 25. We know r is always positive, so now we take the principal square root of both sides of the equation, which gives us r equals the square root of the quantity t squared plus 25. And this is true for both reference triangles. And notice for both reference triangles, the sine of the angle theta, or the ratio of the opposite side to the hypotenuse, is t divided by the square root of the quantity t squared plus 25. And now let's look at our second example. We have sine of inverse cosine of t divided by 3. Again, starting with the inner function of inverse cosine of t divided by 3, this expression is equal to some angle theta that has a cosine function value of t divided by 3. Once again, we don't know whether t is positive or negative. And recall the output of the inverse cosine function is on the closed interval from 0 to pi radians. Because we don't know the sine of t, we don't know if angle theta terminates in the first or second quadrants. To model the angle theta, we'll now sketch a reference triangle in the first quadrant as well as the second quadrant. This would be the angle theta in the first quadrant. This would be the angle theta in the second quadrant. Because the cosine function value is t divided by 3, we can now label the adjacent side t and the hypotenuse 3 in both reference triangles. The first quadrant is when t is greater than 0. The second quadrant is when t is less than 0. To evaluate the composite function, we want to determine the sine of the angle theta. So now we need to determine the opposite sides in both reference triangles. Notice the opposite sides would be y, and in the first and second quadrants, y is always positive, and therefore we know the length of the missing leg will be positive. Let's label the opposite legs y. Using the Pythagorean theorem, we have y squared plus t squared equals 3 squared. And now we need to solve for y. Let's subtract t squared on both sides and write the equation as y squared equals 9 minus t squared. Notice I simplified 3 squared to 9. And now we take the principal square root of both sides of the equation, and we have y equals the square root of the quantity 9 minus t squared. Again, we know y is positive because y is in the first or second quadrant. And now to evaluate the composite function, we want to determine the sine of the angle theta, which is the ratio of the opposite side to the hypotenuse, which you notice in both reference triangles is the square root of the quantity 9 minus t squared divided by 3. I hope you found this helpful.